Hi, our next speaker, Dr. Sean Oliver, our own graduate. I mean, from Mason, graduate from Mason like 4 years ago.
Yeah, 4 years ago.
Yeah, and now is established quantum physicist in MITRE.
Thanks. Yeah, so Sean Oliver, physicist at MITRE, and I'll be talking with you guys a little bit about the quantum sensing research that we're doing. So, by the way, MITRE, at least the location I'm in, is in McLean, Tyson's, right? So if you think about those tall Capital One buildings, we have a pretty large facility over there with 4 buildings and about 4,500 people. So let's see here, a little bit of introduction, right? So as we mentioned, I did my graduate work in Dr. Vora's lab, which was actually a great opportunity to sort of study all sorts of different types of materials, look at quantum phenomena in those materials, visit a number of different, leading research organizations. That was really great. So the beginning of my PhD, I did some work at the Naval Research Laboratory looking at resistive switching with nickel-nickel oxide nanowire junctions, Forster resonance energy transfer in DNA photonic wires. All this is published work, by the way. After that, I moved to the field of 2D materials. It sounds like we're all familiar with, right? So National Institute of Standards and Technology, we were looking at, can you alloy materials to sort of control their quantum properties? We did some work with molybdenum tungsten ditelluride alloys, looking at, can we tune the energy barrier between semiconducting and semi-metallic states? A little bit of valleytronic work, and then spent a little bit of time at Penn State looking at 2D materials again, so alloy, and can we engineer the band gaps of those materials? So a lot of really cool stuff. I graduated in 2020 and moved to MITRE. So I've been there now for 4 years. And my focus has primarily been in quantum sensing, but maybe a little bit about MITRE first, right? So we are a private company that operates not for profit, federally funded research and development centers, as well as an independent research program that we call MITRE Labs. We do a lot of systems engineering related things, specifically what we say to solve complex national problems and global problems. And we like to think of ourselves as bringing an interdisciplinary perspective to the R&D of various topics, right? So our focus areas are things like aerospace, AI, aviation and transportation, cybersecurity, defense, and all sorts of things. A little bit more about that, right? So again, we operate 6 FFRDCs shown in these boxes right here. Maybe it's a little bit small text. I live in this one, which is the National Security Engineering Center. We call NSEC, sponsored by the Department of Defense, for instance, Office of Secretary of Defense, Research and Engineering. We have a number of other interesting sponsors, right? So the Department of Health, we got a Treasury sponsor, Internal Revenue Service, Department of Homeland Security, Federal Aviation Administration, all of these sorts of things. We have over 9,000 employees spread across the world, so 60 plus locations, although the largest one is actually in McLean. They're an excellent recruiter of people that like to do quantum things. Our second largest facility is in the Boston area. We have a ton of lab space. It's a really cool place to visit. Nearly 70% of our staff has advanced degrees, all in all sorts of different topics, which is really cool. You get to work with people with all sorts of backgrounds, and it's really neat to bring people with different expertises onto your project and get really neat perspectives on these sorts of things. Another thing, 25 years of average experience and 12 years of average tenure. I think that really speaks to the fact that people enjoy the work that we do, and they tend to hang out for quite a long time. As I mentioned, I'm mostly sort of in the quantum realm. When I first came to MITRE, we were actually a pretty small group. I joined the Physical Sciences, Nanosystems, and Quantum group, and we only had 11 people. It was like maybe 3 quantum folks, people working on nanotechnology related things, people with chemistry backgrounds, and all this sort of stuff. Shortly after I joined, though, so in October of 2020, we started growing pretty significantly. So we now had 9 members, and we split off into a separate quantum group, the Quantum Technologies group. And then just a year later, added even more quantum folks. So now we have 2 quantum teams, Quantum Technologies group and the Quantum Sensing group with 7 members and 8 members. And I think this really speaks to the interest of the government, right? Well, our client is the government. This really speaks to the interest of the government in quantum technologies. And so it's really exciting. So again, I live in the Quantum Sensing group. I'm here. My group lead is Bonnie Marlowe. We have a chief scientist for quantum technologies, Jakob Weinstein. And my group consists of people with all sorts of quantum backgrounds, right? So superconducting sensors, atomic sensors, quantum materials, and all of these sorts of things. So what does our research at MITRE look like? So we have sort of 4 focus areas: quantum computing, post-quantum cryptography, communications, and sensing. Again, I focus here. We have people looking at quantum computing. So can you use this tool to break asymmetric cryptography? Can you use this for efficient machine learning and for materials discovery? In the case of post-quantum cryptography, can we develop asymmetric cryptography that is robust against quantum computers should these things become available? So essentially, can we have algorithms that protect our sensitive data if people have access to a quantum computer? Quantum communications, right? So developing provably secure data transfer, enhanced clock synchronization, and in the case of quantum sensing, developing sensing modalities that have smaller swaps. So when we say swap, we mean size, weight, and power characteristics, and also enhanced performance too. So in terms of quantum sensors, what we're trying to do is leverage quantum phenomena to measure things like magnetic fields, electric fields, time and frequency, acceleration due to gravity, and inertial acceleration. And when we talk with our various clients, the things that we like to say are that sensors based upon quantum phenomena offer improved performance, improved swap, so better size, weight, and power characteristics, and then also novel capabilities. And one of the sensors I'll talk with you guys about in this work will sort of touch on all of those things. A little bit about sort of how we go about our research and development in MITRE. We take a systems engineering approach. So we do sort of an interdisciplinary collaboration of people across the entire R&D pipeline, beginning with basic and applied researchers, or people like, the academic world, the component manufacturers, across the tech manufacturers, the system integrators, all the way to the consumers and the end users. Basically, whenever we invest in developing a technology, we want to make sure that all along the way, we have the end users in mind. So when we reach that final product, it finds its way out of the lab into someone who's actually using this without sort of barriers along the way, right? And so we really are bringing together people from all of these different spaces, right? So the quantum physicists like ourselves, electrical and microelectronic engineers, mathematicians, system integrators, the operational experts, so the people that are familiar with the applications, and the end users. And we ask ourselves questions like, do the requisite component technologies already exist? So let's imagine that I'm building a device, a brand new device, and it takes special components. Do those components exist? Or do we need to advocate for development of those sorts of components because we have sort of a way to speak to our government sponsors? We can advocate for funding for those sorts of things. What performance metrics are required to meet the need of the specific applications that we're aiming for development of these quantum sensors? What are the system integration requirements? So swap, ruggedization, ease of use. Oftentimes when you develop a sensor, it won't be operated by, say, graduate students, PhD level trained people, but rather maybe like an 18-year-old person in the Navy or something like this. So these devices need to be easily used. And then lastly, who are the stakeholders and the end users for their technologies and what are the needs? So we're trying to answer all of these questions to really tell us, hey, this is something worth going after and trying to answer these all along the way. And so jumping back to the plot that I showed you before, this chart, we have work in my organization across all of these spaces. And I'll talk with you guys specifically about some work that I've been leading for the last couple of years where we're developing solid state defect sensors. So the tool that I've been developing, we call the quantum diamond microscope. You'll see me refer to it as the QDM in these slides. This has been some work that has been funded through our internal R&D efforts for about 5 years now, and has also been funded by various government sponsors. And we've also worked with academic folks. So my main collaborator is Ronald Walsworth. You guys may know him from Harvard, University of Maryland. Done some work with MIT, and then a number of industry people just to make sure that we really have this tool sort of worked out in terms of who will be using this in the end. Right, so the tool that we've been developing, the quantum diamond microscope, leverages nitrogen vacancy centers in diamond. I imagine maybe you guys have heard of these before. These are a point defect in diamond. It's characterized by a substitutional nitrogen atom and then a lattice vacancy in the carbon lattice of, in our case, a lab-grown diamond. The vacancy can take the place of, say, the upper left or the upper right, bottom left or the bottom right of a nitrogen atom. And so we'll have an ensemble of these nitrogen vacancy centers across this special diamond chip. An image actually shown right here. This is a pair of tweezers, so you can kind of get a feel for how big these are. So we have millions of these, an equal distribution of the NV centers in all of these axes spread throughout this diamond. There's 4 possible orientations, as I mentioned, and what this lets us do is measure the vector components of magnetic field, right? So the magnetic field, not only does it have an intensity, but it also has a direction, so we can measure the directionality of that field. And these NV centers, they have magnetically, electrically, and thermally sensitive spin states. We can read all of this out optically, so it's a really great solid state platform for sensors. I don't want to spend too much time on the physics, but what we do is a combination of excitation with green light and then monitoring red fluorescence. So essentially exciting those electrons up into their excited state. As they relax, they emit a red photon. And what we do is we monitor that. Now, they're typically in the spin 0 state, but there's a plus and minus 1 spin state. And that energy state, those energy states are energy degenerate, but in the presence of a magnetic field, we'll experience a Zeeman splitting, and we can monitor that Zeeman splitting to basically pull out the vector components of a magnetic field. So if we use a microwave drive to drive from spin 0 to the plus and minus 1 state, the plus and minus 1 electrons will tend to decay through this pathway that emits an IR photon. And so what we'll see is sort of a dip in fluorescence as we're monitoring the fluorescence of the diamond, and that will let us read out the magnetic field components. And so NV center physics and sort of applications and all this stuff has been around for quite a long time. I think it was early 2000s. And so it's really experienced sort of a wide swath of researchers really, proving out the science, and we're kind of now in this advanced prototyping phase. In fact, a lot of these types of sensors are being commercialized for a number of applications, and we sort of have our eye on all of these things. For instance, you can use this for magnetic navigation. So you can imagine that you have some platform in a GPS denied environment where, say, your navigation platform is being jammed, or you might be underwater or something like this. You can use the magnetic field components to do navigation. Anomaly detection, right? So magnetic fields like to penetrate through materials and through water and these sorts of things. So you can detect anomalies with these sensors, and the vector capabilities really let you gain more information about what you're trying to look at. Condensed matter physics, imaging of cells, imaging of geological samples. So this is really leveraging the capability to do magnetic field imaging. And this is actually what I'll share with you guys in the following slides. And some really great things about sensors based upon NV centers is, I already mentioned vector field sensing. The ability to measure the vector fields is dependent upon fundamental constants, and so it's really a calibration-less measurement. High dynamic range, right? So we don't need very careful shielding of our sensor. We can place this thing in sort of intense environments, and we can also measure large ranges of magnetic fields. It's a robust solid state platform, good resolution in terms of magnetic imaging. It operates across a wide range of temperatures, from near cryo temperatures up to, say, 1,000 Kelvin. Wide pressure range operation, right? It's diamond. And actually, surprisingly low laboratory costs. So the sensors that you'll see in the following slides have been built for roughly around 50K, which is great. So what do we care about? What's the reason why we care about this technology at MITRE? We are developing a magnetic imaging tool to capture magnetic fingerprint of microelectronics for reasons of integrated circuit security and assurance. So you can think about it this way, right? So the microelectronics that you say have in your cell phones, our computers, and all of the devices all around us, fabrication of those devices is mostly done overseas. It's an extremely complicated process that sort of needs to go to a bunch of different places. And the United States has really sort of moved that away from stateside, for the past 25 years or something like this. And we're still really starting to realize that was a mistake. The thing about having the supply chain overseas is that adversaries have access to these devices as they're being made. And they can do things like implement Trojans in your device or implement counterfeit components, right? So a Trojan device is something that may be put into a hardware component and may leak sensitive information. The counterfeit device may reduce the amount of time that a device can survive across its timeline. For instance, in the case of counterfeits, for instance, there was a couple of years ago, a F-16 pilot who passed away whenever he tried to eject from his fighter craft, and the ejection seat failed. They did some reverse engineering and looked at those devices and found that they incorporated counterfeit components into that seat. And so that's a serious deal. And of course, Trojans, right? If these sorts of things are find their way into critical components, let's imagine government computers or cell phones or financial devices or healthcare devices or these sorts of things, we can't allow people to have access to that sensitive information. And so what we've been trying to do is develop a magnetic imaging technology that can detect these sorts of anomalies. And then another thing too, can we detect failures in devices through the magnetic fingerprint? So our device looks something like this. We have this diamond chip, about 5 by 5 millimeters, so rather small. It's grown in a lab. And the special sauce is that we have a very, very thin layer of those nitrogen vacancy centers. It's key that they're in a very thin layer. Millions in all of those sorts of orientations I was talking about before. And then what we do is we can place that diamond right on top of the sample. And then through a combination of laser plus microwave loop, we can drive those NV centers into their sensing state. They'll emit a magnetic field dependent fluorescence. We collect with an objective and literally just image with the camera. It's a pretty simple device, actually. This is a prototype of it at one of our labs at MITRE. We've got 4 currently for all sorts of different things. We're looking at fast imaging techniques, advanced quantum protocol, control protocol techniques, and then sort of our vanilla QDM that we call this. This is one of the integrated circuit chips that we're measuring. We've removed some of the epoxy packaging here, so you can see the top metal layer of the devices. And this is an image of the diamond sitting right on top of that sample. And so in order to sense a magnetic field, essentially you'll have some magnetic fields that are coming from the device that you're trying to measure. They'll interact with the NV centers in their in the diamond. This changes their optical emission, and then we just take a picture of that. So the way the data sort of comes in looks something like this. So we do what's called optically detected magnetic resonance spectroscopy, where we're monitoring the fluorescence of the diamond as we apply a microwave frequency. And we do this on a pixel-wise basis across the whole diamond chip. And what we end up with a spectra like this for every pixel on the camera, where what you're looking at here are dips in the fluorescence associated with the transition from spin 0 to plus and minus 1. We have 4 pairs of peaks here associated with the 4 orientations of NV axes I was talking about before. And so what we can do is essentially back out the vector components of the magnetic field. So this separation between these, right? So this is one pair given by this blue arrow here, and then another pair given by green, for instance. So the separation between those resonance features is proportional to the magnetic field projected onto each of those NV axes. And through a combination of some equations, we can go from the diamond lab frame to the lab frame of the diamond frame to the lab frame magnetic field images. And what we end up with are simultaneous magnetic images of the X and Y components of the magnetic field. So those are going to be the in-plane components and the out-of-plane component of the magnetic field. And we get all of these simultaneously and in a wide field sort of microscopy scheme. And what's really cool about this, right, is traditional sensors there's a lot of people that use sensors to do this sort of microelectronics characterization. They typically require raster scanning, which takes quite a long time. And they also are only sensitive to the out-of-plane component of the field. So they would see only something like this. And our ability to measure those vector components of the field lets us gain additional information of what's going on in the chip and helps us detect some new things. So what you're looking at in these images is a printed circuit board that we had developed specifically for this technology, just to say, hey, does this work? So these blue traces are in the top layer of the PCB. They then go through some vertically oriented vias down into 3 different depths. And what we do is we just bias this center trace and we collect these images. And so you sort of see, like in the DZ magnetic field image, the reverse polarity on opposite sides of the path. You can kind of think of like the right-hand rule for magnetic fields in physics 1 or whatever it is. And in the BY image, we can actually detect current as it's flowing through this via, which is something you couldn't do previously. So that's really exciting as microelectronics are sort of going to a more advanced architecture. You can think 3D integrated circuits and these sorts of things that you see in the state-of-the-art devices. So that was measurements against kind of a test chip that we made in the lab. And we said, hey, can we use this against real devices? So we have a field programmable gate array that we wanted to test against, right? So this is a chip that we're measuring. This is just an optical image. You can think like if you opened a cell phone or something and you see the black integrated circuits on a motherboard, for instance. This is an image of that. X-ray image showing the silicon die here, and then cross-section SEM images where the packaging, the black packaging is about 500 microns thick. You can see the silicon die. This is a zoomed in image, right? So these are the transistor levels, and then these are the metallization layers that are delivering power to those transistors. So we can remove that epoxy packaging. This is just an optical image, and place the diamond immediately right here. And then we program activity to be present on this chip in these different regions labeled R1 through R4. So what we program in this case are ring oscillators, which are essentially just switching transistors. And because we have full control of those switching transistors, we can kind of step down how much activity is occurring on that chip. So in this case, 200 ring oscillators active down to 5, and then a single ring oscillator active, where these images, what you're looking at are magnetic fingerprints, right? So red is plus magnetic field, blue is minus magnetic field. And what we find is that we can easily detect activity and say, hey, it's right there, which is a huge deal, right? So you can imagine if you were an analyst trying to characterize a chip, the typical technique goes electrical, like current voltage measurements, maybe some other things, kick it over to a scanning electron microscope, where essentially you're trying to scan billions of transistors in a scanning electron microscope. How do you even know where to start? And so being able to say, hey, look there, that is a huge win. I think like the current ceiling for reverse engineering for a 1 centimeter by 1 centimeter die on a 65 nanometer node, which is sort of legacy technology, it's like something like a year to fully process something like that. And so if you can detect and local, so this is by the way, a 28 nanometer process node chip. If you can say, look here, it's huge, huge win. So I mentioned at MITRE, right, we get to work with all sorts of people. That was work that we did with our guys over at Harvard, now University of Maryland. This is work that we did with NVIDIA. So we brought the tool to people in industry and we're curious to get their thoughts. And so the NVIDIA guys sent us a GPU, which was really exciting. This was during COVID when nobody can get GPUs. And they're like, hey, here's some, which was awesome. And they gave us a sort of poor resolution in this image, but this is a CAD layout. And they said, can you measure these current paths located here on this chip? And so what we do is we bias this one trace, and we take these magnetic field images, and then we go back to NVIDIA and say this is what we can do. They're super excited about this. They use a scanning square microscope in their labs. So again, they got a raster scan. This tool fits cryo and all these things. And honestly, everybody hates using that tool. So the fact that we can gather this stuff without cryo and we get these vector images and all this was really exciting to them. And one really exciting thing too, right? So here in this BY image, we could detect current in a protection diode that you can't see in the BZ magnetic field image. And my apologies there, so the resolution isn't very good on the screen. But that's a big win for if you're trying to do failure analysis or something like this, where you just can't see things because you're limited by your instrumentation. And so here, you're really seeing quantum sensing being able to shine in the sense of providing new capabilities to the user. A little work we did with MIT, right? So we wanted to say, could we detect Trojan hardware on a chip? This is sort of an academic implementation where we went to University of Florida. They have this really cool thing called Trust Hub, where they put versions of Trojans onto this database and let you program them to be active on chips. So that way you can explore how your emerging sensor might fare against these sorts of things. And what we find is that we could easily detect this sort of stuff. So this magnetic field image is with no anomalous activity present. And we sort of just see the noise floor. And then as we program the Trojan to be active, we find that we can easily detect and localize. Again, localize is the key thing here. We get a really neat opportunity to capture spatial plus temporal information, which you can't do with other sensors. And because we had full control of the Trojan active on this chip, we could control sort of operational parameters. And we find that we can scale it down to just a fraction of a percent of the total system logic. So, right, if you think billions of transistors, 0.5% of that of those transistors are active, and we can still detect that. So that's great. like I'm running short on time, so just, right, so we put together some relevant performance metrics for the QDM against the microelectronics application space. And one thing I want to point out, right, so like, as I mentioned, we put a lot of work into engaging with people across the entire R&D pipeline with hopes of developing a tool that will become available to other folks. And so in this particular case, for instance, in working with Harvard and University of Maryland, we generated some patents. At MITRE, if you generate some patents, you get a lot of incentives to do this sort of thing. You get some money back, and then every time that the patent is licensed, then you also get paid too. So that's really cool. So there's a lot of incentives to do that. We ended up patenting this technology, and then out of that came QDM.io, which is a startup company from Quantum Catalyzer. It's a quantum startup incubator by Ron Walsworth's group out of the University of Maryland. And so this technology is now available and can be purchased not just for microelectronics testing, but also for things like 2D materials research, just materials research in general, bio research, and all these sorts of things. Yeah, and so in conclusion, right, I gave you guys a glimpse about some of the quantum sensing efforts that we have at MITRE with QDM as an exemplar. We really sort of have a neat opportunity to keep our fingers on the pulse of emerging technologies, and then talk to government people who say, hey, these are our needs, and then connect those two things, and then bring together an interdisciplinary team. In this particular case, we've got our quantum physicists, our microelectronics guys, mathematicians, and hardware security experts, and operational analysts. Bring all those guys together to successfully create a new technology that we can accelerate its transition out of the lab into the hands of users. That's it. Thanks much.
So what makes nitrogen frequency really promising for your application? Because I think for quantum computing, for example, I think I have clear understanding of what pros and cons for each candidate, like MB center, topological insulator, spoken circuits, quantum dot, whatever. But for this specific sensing application, what makes MB center interesting here?
Yeah. So one, ultra long coherence times at room temperature. We don't have to use cryo. That's awesome. The vector capabilities, so like silicon carbide, for instance, you tend to only be able to measure, I'm talking about defects in silicon carbide, only one component of the magnetic field, so that's another win. And it's really those two things. Yep. The room temperature operation, ultra long coherence times.
So you're like the other team working on quantum computing, do they also work on the same platform? Or?
They work on all sorts of things. Really, our quantum computing efforts currently at MITRE, we have few different things going on, but our main one has been, is it going to work? And then also, what are the applications? Everyone's always going to have those questions, I mean, like in the case of our sponsors, not a single application has really shined and said, hey, we're going to get some big wins. And so we do a lot of performance tracking and benchmarking and these sorts of things. In terms of, are they using the same materials? So we have another effort that we call our Quantum Moonshot. They're working on developing some hardware related to this sort of stuff, and they're using nitrogen frequency sensing diamond. Jerry Gilbert, are you familiar with the name Jerry Gilbert? Okay. Yeah. So I can send you some stuff on that. They have a pretty cool collaboration with them, Sandia and Dirk Ingram's group at MIT.
Is the QDM device able to see what type of activity it's detecting? Like, is it whether it's like a failure or intrusion, or does it just detect an activity and like ask people to take a look at it?
Yeah, it's sort of like that, right? So if you're looking for something like failures, you could imagine, like, so let's say that you are scanning devices on the fab line. You would have a feel for what the golden operating circuit looks like, and then just comparing these images. So if you might see some current flow that's abnormal, you could say, hey, there's some failure here. In the case of detecting anomalous activity for things like Trojan hardware and this sort of stuff, you're sort of just looking for, hey, do I have some hot spot? Now we're gonna have to kick this over to a reverse engineering team.
But I have noticed that with the quantum computing in general, it's bigger for electron spin, but I think Dr. Wolf was actually looking to use, nuclear spin.
Yeah, absolutely.
So do you see yourself kind of entering that way, or sticking with electron spin, like it's, is there a reason to stay with electron?
Yeah, you're totally right, by the way. Yeah, Ron has been doing a lot of work on pushing that for, they got a startup company called QDTI, Quantum Diamond Technologies Inc. that does like bioassay and these sorts of things. We are thinking about implementing some of these pulse protocols, kind of like what they do. Yeah, because that will let us gain, significant wins in what sort of fields we can measure. So that will improve our sensitivity, improve our ability to do things like, say, detect AC fields and these sorts of things. So yeah, we have that in mind. And I had mentioned before that we have 4 of these tools in-house. We actually have one dedicated to trying to implement some of these advanced techniques.
It's pretty cool. NMR, like, eventually problem is like a massive thing. I don't know, so, I mean, is the coherence is on, you know, is that the room temperature measurements? I imagine in are you doing all of that?
Yeah, room temperature. Yep, it's all room temperature. What's, I knew I should have expected something like that from you. Any other questions? Cool. I'll be hanging around if you guys want to chat tomorrow. Oh,
You have a simulation. What kind of